Hello everyone, my name is Stu Adler. Welcome back to Introductory Lectures in Thermodynamics. So far in the course, we've focused mainly on how workers describe the behavior of groups of molecules at equilibrium, focusing mostly on data with little theory. This was important for establishing the types of phenomena we hope to understand and predict. In other words, the question was what? The purpose of this episode is to begin addressing the question of why. Why do molecules behave as they do, and how do we understand and predict this behavior? As we saw in the example of the Haber-Bosch process, there are essentially two issues we need to address to answer this question. The first is how systems of molecules transform upon changes in internal energy content. The second is the issue of probability, which influences the average way in which molecules are likely to be arranged in a system. This is a lot to cover, so for the moment let's focus on the energy part. What energy are we talking about, and how does this energy relate to the configuration of molecules within the system? To begin, let's clarify what energy we're really talking about. There are lots of different types of energy, which can include energy possessed by individual or groups of molecules, as well as energy possessed by an entire system due to motion, gravity, or other forms of potential energy. As an example, when a pitcher throws a 105-mile-an-hour fastball, the kinetic energy acquired by the ball is about 160 joules. If by chance a batter connects and sends it high enough to clear the ballpark, that involves about 140 joules of gravitational potential energy. I'm sure to the catcher this feels like a lot of energy. However, to put things in perspective, the energy required to heat up the baseball from absolute zero to 300 Kelvin is about 90,000 joules. So even if we considered the kinetic energy of the ball in motion to be part of the system energy, it would be pretty small potatoes, even for Aroldis Chapman. More importantly though, when a baseball is thrown, the added kinetic energy imparted to the molecules in the baseball is a coherent form of energy that remains largely decoupled from the motion of the molecules inside the ball. Upon being caught, this energy is mostly transferred back out of the ball again, so never really becomes incorporated as part of the molecular level energy influencing the thermodynamic properties of the ball. For this reason, in chemical engineering, we usually treat energy associated with gravity and whole body motion of fluids as a separate problem, coupled weakly to molecular energy via some kind of friction factor. You'll learn more about this in Chemi 330. The part of the energy we usually care about in thermodynamics is the energy associated with random motion and arrangement of the molecules. This part of the energy is usually called the internal energy, symbolized in our text and in these notes by the capital letter U. Internal energy is extensive, but like many other properties, we can also define an intensive molar or mass-specific internal energy, symbolized here as U or U hat. The internal energy is often subdivided into kinetic energy, EK, which is possessed by individual molecules and is closely associated with temperature, and potential energy, which is more of a latent or hidden form of energy that depends on the arrangement of molecules within the system. To illustrate the importance of potential energy in thermodynamics, consider for a moment the following two photographs involving large crowds of people. One is the famous Shibuya pedestrian crossing in Tokyo. The other of an Austrian ballroom in Vienna. In both photos, we see a lot of people in a relatively small amount of space. But if you look carefully, you'll notice there's a big difference. At the crossing, we see a lot of people heading in different directions, not really talking to each other, looking ahead, or down at their cell phones, only interacting with other people as needed to avoid a collision. In contrast, the attendees of the ball have formed an organized structure, involving pairs of people dancing, and we can see people in the background interacting and talking to each other, enjoying the music and each other's company. Of the two photos, which do you think better analogizes what molecules do in condensed phases, like the ones we've been discussing the last week? If you picked the Viennese ball, you probably made the right choice. Think about it this way. Imagine all molecules were like pedestrians at a large complex intersection, flying in a straight line through space, only interacting with each other via collisions. At any finite temperature, the molecules would just scatter in all directions, unless constrained in a finite volume, in which case they would just be a gas. The only way for them to form condensed phases and exhibit all the interesting phenomena we've been discussing the last week is if they have some sort of attractive energetic interactions that cause them to bind together and form complex structures that compete with their natural tendency to just scatter. In fact, it's really the potential energy between atoms and molecules that gives rise to most of the interesting phenomena in the universe. Without it, the universe would just be a big homogeneous gas. Think about how boring that would be. Luckily for us, matter behaves more like people at a dance. So what are these attractive interactions? How do they work? And how do they result in what we see in condensed matter? First, I think it's worth recognizing that molecules themselves are already a product of attractive bonding interactions between atoms. However, atomic bonds tend to be so strong, short-ranged, directional, and quantized, we usually don't describe them as a continuously variable energetic interaction. For example, we don't treat H2O as H and O atoms attracted to each other by a force. Under ordinary conditions, H2O forms a quantized unit with well-defined stoichiometry, structure, and properties. Understanding these bonding interactions among atoms is really what chemistry is all about. But on top of these very strong bonding interactions, molecules exert additional forces on each other via short-range, electromagnetic, and electron overlap interactions that strongly influence their behavior as gases and dominate their behavior as condensed phases. In Chapter 4 of our text, the author Milo Koretsky walks us through the origin of some of these forces. But let's try to summarize some of that here as well. One of the simplest interactions to understand from the perspective of classical physics is direct dipole-dipole interactions. Although by definition molecules represent an electrically neutral species, i.e. no net positive or negative charge, many molecules have a structure in which positive and negative charge is laterally distributed, resulting in a net electric dipole. If a molecule tumbles randomly through space, the average dipole that other molecules see is zero. However, like everything at a molecular level, it's all about statistics. As molecules with electric dipoles approach each other, the electric field generated around them by their dipoles biases the average dipole orientation of the other molecule, causing a slightly higher probability that the adjacent dipoles will be anti-aligned, and thus attracted to each other, a bit like oppositely oriented magnets. This results in a net average short-range attractive force that gets stronger at lower temperatures and is related to the dipole moments mu I and mu j of each molecule. This force is most relevant for molecules with very asymmetric structures, which result in a strong dipole, such as water, HCl, or a partially halogenated hydrocarbon, like difluoromethane. One way to characterize this force is in terms of the potential energy required to separate the two molecules. Defining this energy as zero when the molecules are infinitely far away, this energy becomes negative as the molecules approach, scaling with distance as 1 over Rij to the sixth, where Rij is the center-to-center distance between the two molecules. If they get too close, however, their electrons begin to overlap, causing a sudden jump in potential energy. This corresponds to an even shorter range repulsion between the two molecules that prevents them from occupying the same position in space. The net result is a minimum in potential energy when the molecules are adjacent but not overlapping. When the molecules are separated by an appreciable distance, the potential energy returns to its maximum of zero. Many molecules have no dipole. However, an interesting quantum mechanical effect of electrons is that when a molecule is exposed to an electric field, it alters the symmetry of the potential profile around the molecule, breaking the symmetry of the electron wave function and causing it to acquire a dipole. Thus, when a molecule I without a dipole is near a molecule J which has a dipole, the field around molecule J induces an oppositely oriented dipole moment in molecule I. This results in a net average short-range attractive force called an induced dipole interaction that is related to the polarizability of molecule I and the dipole moment of molecule J. This force is most relevant for pairs of molecules where one has a strong dipole, like water, and the other has loosely bound and thus polarizable electrons, like CCl4, or both in the case of some molecules, such as nitrobenzene. Just like direct dipole-dipole interactions, induced dipole interactions scale as 1 over Rij to the 6th power, so are also short range, and involve a minimum in potential energy for adjacent but non-overlapping molecules. Taking quantum mechanical effects one step further, it turns out if you have two molecules I and J, neither of which have dipoles, when they come close to each other, adjustment of the electron wave functions to the broken symmetry around the individual molecules causes them to acquire correlated dipoles. This results in a net attractive force called a London dispersion force, named after the German-American physicist Fritz London, which is proportional to the polarizability of the two molecules and scales inversely with the average of the reciprocal ionization energies of the two molecules. This force is most relevant for nonpolar and/or highly polarizable molecules, such as CCl4 or benzene. In general, the polarizability of a molecule scales with its size and number of electrons, so tends to dominate for larger molecules, like hydrocarbons. But guess what? The potential energy profile associated with this force scales as 1 over Rij to the 6th, just like direct and induced dipole interactions. Taken together, direct dipole, induced dipole, and London forces all comprise components of what workers call van der Waals forces, short-range attractive forces that exist between any two molecules, with a potential energy that scales inversely with the intermolecular distance to the 6th power, and involves a minimum in potential energy for adjacent but non-overlapping molecules. Besides van der Waals forces, another important force that attracts molecules together is what is generally referred to as chemical interactions. Some molecules, when they approach closely enough, begin to share electrons in a manner similar to chemical bonding, in some cases even exchanging atoms between them. A prominent example is hydrogen bonding, which is an exchange interaction involving the protons on one molecule with exposed lone pair electrons on another molecule. In pure water, for example, we know that at any time about 2 out of every 1 billion molecules will have an extra proton forming H3O plus ions, producing the same number of OH minus ions. This chemical exchange of protons is actually just the tip of the iceberg. Every time a water molecule comes near another water molecule, they begin to share one another's protons at some level as a precursor to full exchange. This exchange interaction is favorable energetically, leading to an enormous attractive force, much stronger than the van der Waals interaction. This explains why tiny molecules with relatively weak van der Waals attraction, like water or ammonia, can exist as liquids at relatively high temperatures. Other prominent examples include proton exchange between alcohol and/or carboxylic groups, or proton exchange in sulfuric acid. Note that regardless of their origins, intermolecular interactions between any two adjacent non-overlapping molecules is always attractive, even for molecules that macroscopically don't seem to like each other very much, such as oil and water. The reason oil and water don't mix is not because they repel each other. H2O has a strong dipole, and oil contains nonpolar but large, highly polarizable molecules. Thus, there is going to be a strong, attractive, induced dipole interaction between them. So why do they separate? The issue is what they separate into. Water on its own has incredibly strong hydrogen bonding and direct dipole-dipole interactions, and oil has very strong London dispersion forces between the large polarizable molecules. These interactions between like molecules are much stronger than the heterogeneous induced dipole interaction between oil and water. So given a choice, the molecules as liquids tend to self-segregate into two phases where the energetic interactions are more favorable. This is one of the things we'll try to understand more quantitatively over the course of this quarter. One simple model workers often employ for understanding the consequences of intermolecular interactions is something called the Lennard-Jones model, which we explored briefly in a previous episode. According to this model, the interaction of any pair of molecules in a group contributes negatively to potential energy, with a value related to the distance r between molecules. This potential energy function, called the Lennard-Jones potential, is composed of two terms, a short-range negative term that scales as 1 over r to the 6th, representing van der Waals or other attractive forces, and an even shorter range positive term that scales as 1 over r to the 12th, representing intermolecular repulsion. Unlike the attractive term, which is grounded theoretically in the van der Waals forces, the repulsive function is entirely empirical, chosen for its very short range and mathematical simplicity as twice the exponent on the attractive term. The Lennard-Jones potential has two parameters, epsilon, which represents the depth of the potential, meaning the energy required to separate adjacent molecules to a distance of infinity, and sigma, which is the distance between molecules at which the attractive and repulsive terms are balanced. The minimum in potential energy occurs at a distance of about 1.12 sigma. How do molecules behave when subject to a Lennard-Jones interaction? This was a long-standing subject of research in the 20th century, a central focus of an area called statistical mechanics, which seeks to understand average statistical behavior of molecules subject to various constraints. Unfortunately, we don't have time in this course to cover this subject adequately. Instead, let's take advantage of the monumental advances in computers that have taken place over the last 2 decades to see for ourselves. We can do this using a computational simulation technique called classical molecular dynamics, or MD for short. In this technique, we treat each molecule as an infinitely small mass m, which has a position vector x and velocity vector v. At any moment, we can calculate the change in position of each molecule with time based on its velocity at that moment. At the same time, we can calculate the change in the velocity of each molecule with time based on Newton's second law of motion, force equals mass times acceleration. The total force vector on each molecule is a sum of the forces exerted on it by other molecules. In accordance with classical physics, the force exerted by any molecule on another can be calculated as the spatial derivative of the potential energy interaction between them. The derivatives dv dt and dx dt are then integrated forward in time using a method called the Verlet algorithm. Shown here is a molecular dynamics simulation applet written by Dan Schroeder at Weber State University in Utah that simulates up to 2,500 identical molecules subject to Lennard-Jones interactions in an isolated two-dimensional box. This applet is free to access and is available at the link in the description. In this simulation, the equations have been non-dimensionalized by scaling distance to the Lennard-Jones parameter sigma, time to sigma times the square root of mass over the Lennard-Jones parameter epsilon, energy has been scaled to epsilon, temperature to epsilon divided by the Boltzmann's constant, and pressure to epsilon divided by sigma cubed. As I'll show you in a moment, this makes it easy to understand what we're calculating in terms of the Lennard-Jones interaction. As with any isolated system, we only have control over 3 things. The first is the total number of molecules, n, which we can vary from 1 to 2,500. The second is the volume of the system, v, which we can adjust by changing the size of the square box containing the molecules, measured in numbers of molecular diameters. Note that because this is a 2D simulation, volume is an areal volume equal to the square of the size of the box. Likewise, the surface area of the inside of the box is a lineal area equal to 4 times the box size. Finally, we have control over the total energy of the molecules, U, symbolized here as E, which is adjusted by setting the molecules into motion and then increasing or decreasing the velocity of each molecule along its current path by a certain percentage, using these buttons here. Unfortunately, we cannot prescribe the total energy, but because energy is conserved, we can adjust it up and down to its desired value, and it will stay constant after that, provided our choice of time step is short enough to integrate the laws of motion accurately. During the simulation, the applet calculates several useful things. The first is the time counter, which tells us how long the simulation has been running in scaled units. The second is total energy E, measured in units of epsilon. We can also calculate the temperature T, defined here as the total kinetic energy divided by the total number of molecules, n. Finally, reported here is the pressure, defined as the scalar average momentum transferred to the walls of the box per lineal area per time, also expressed in scaled units. To begin, shown here is a group of 492 molecules that have a lot of kinetic energy, the equivalent of 5 epsilon per molecule. After reaching equilibrium, the molecules are scattered throughout the container. Slowing down the simulation, we see that the molecules behave a lot like the people in the photo of the Shibuya intersection, primarily interacting with each other through collisions, otherwise remaining on a straight, uninterrupted path. If we calculate the total kinetic energy by multiplying the temperature times the number of molecules, we get 2,490, only slightly higher than the total energy in the system. This means that we only have about minus 10 units of total potential energy, or about 0.02 negative epsilon per molecule. In the absence of any significant potential energy, the system behaves rather like our idea of a gas, albeit a very dense one in this case. If it is a gas, we might expect it to obey the ideal gas law. One way to test this is to change one of the phase-intensive properties and see if it does. Currently, we have a temperature of 5 and a pressure of 0.26. So let's reduce the number of molecules to 246, which is half the previous number, corresponding to a doubling of the molecular volume. According to the ideal gas law, the pressure should fall in half. Indeed, we see that when the system stabilizes, the pressure is now 0.13, half of what it was at twice the density. Increasing temperature now from 5 to 10, while keeping density fixed, we see the pressure returns to 0.26, again obeying the temperature dependence of the ideal gas law. What this tells us is that the ideal gas law behavior is really a consequence of random motion of molecules in the absence of any significant potential energy. In contrast, let's now look at a system with 492 molecules that has no kinetic energy, corresponding to 0 absolute temperature. As you can see, the calculated temperature and pressure are 0. However, the total energy is approximately minus 1500. This can be understood by looking at the structure, which satisfies our traditional understanding of a solid, something having long-range order of the atoms or molecules. In this case, the molecules have adopted a hexagonally close packed structure in which each molecule is surrounded by 6 nearest neighbors. Since we are at 0 Kelvin, we expect the distance between each molecule to be 1.12 sigma, corresponding to the minimum of the Lennard-Jones potential. Indeed, we can see a small 12% gap between each molecule, which have been drawn with a diameter corresponding to 1 sigma. For each molecule, there are 6 nearest neighbors, for a total potential energy of minus 6 epsilon among these molecules. Multiplying by 492 molecules and dividing by 2, so we don't double count each interaction, we expect a total energy of about minus 1476, not counting the exposed surface or interactions of next nearest neighbors. The actual value here is close to that. So what we're seeing here is a system that is near a minimum in potential energy. Okay, so now let's add some kinetic energy back in. We can do this by grabbing the molecules with our mouse and giving them a toss. After the system reestablishes equilibrium, it looks like this. The total energy is now about minus 500. So we have apparently added about 1,000 units of total energy. But what form is this energy? We expect it to be composed of 2 parts, potential energy and kinetic energy. The calculated temperature is about 0.4, which after we multiply by the number of molecules corresponds to plus 200 units of total kinetic energy. But the system is increased in total energy by 1,000 units. That means that 800 units of this additional energy must reflect an increase in potential energy. One way to prove this is to pause the simulation, reduce the simulation speed to a minimum, then freeze the motion of all the molecules, corresponding to removal of all kinetic energy in the system, and then resume momentarily to recalculate the energy. We see that the total energy is now about minus 700, 200 units lower than we had when the molecules were in motion, confirming we had 200 units of kinetic energy. This means that in this system, the potential energy is 700 units lower than we had when all the molecules were moving around randomly. In other words, negative potential energy is associated with partial aggregation of the molecules, even in a dynamic state of motion. At this point, the molecules are acting a bit like the folks in the Viennese waltz, some closely associating and interacting with each other, others less so, but with a definite structure that is not entirely random. To take this one step further, we can run a series of simulations varying molecular volume, defined as the areal volume divided by the number of molecules, adjusting total energy until the equilibrium temperature reaches a prescribed isotherm, and then calculate pressure. Shown here is the result for T equals 0.6. As you can see, at high molecular volume, corresponding to low molecular density, log P versus log V has a slope of -1, corresponding to the ideal gas law. Comparing to a plot of potential energy per molecule, we see this behavior corresponds to a region where the potential energy interactions are very weak. However, as volume is reduced, the potential energy becomes increasingly negative, going from 0 to a value approaching -1 epsilon per molecule, corresponding to each molecule being adjacent to about 2 molecules on average. This trend corresponds in the PV diagram to a negative deviation in the pressure from the predictions of the ideal gas law. Finally, as volume is decreased further, something odd happens. The pressure begins to increase again, eventually exceeding the predictions of the ideal gas law. However, over the same range, the potential energy continues to become increasingly negative. How can we understand these trends? Perhaps some insight can be gained by examining the following simulation, which shows a regular array of molecules at 0 temperature. In this case, we've removed all kinetic energy and packed the molecules together so they have lots of attractive interactions, as reflected in the large and negative total energy. Starting the simulation and then stopping again after a few time steps, we see the molecules in the middle of the mass of molecules are relatively undisturbed despite strong attractive interactions with their neighbors. This is because the average force on each molecule is 0 due to the symmetry around each molecule. However, near the inside surfaces of the box, this symmetry is broken. We see molecules near the surface being pulled backward into the bulk by the molecules behind them. Over subsequent steps, we also see another effect. The acceleration of the molecules is blocked by adjacent molecules, suggesting crowding might also have an effect on the pressure if the kinetic energy is non-zero. The first person to put this together was the Dutch physicist Johannes van der Waals, who used a mean field approach to understand how potential energy and molecular crowding should affect pressure in a gas. Recall from classical physics that a force acting over a differential distance dx corresponds to a differential input of mechanical energy. Converting force to pressure times area, and dx to a differential change in volume divided by area, we can relate the applied pressure to the derivative of mechanical energy with respect to volume. Examining a plot of the log of the potential energy magnitude calculated from our simulation versus the log of the volume, we can see that at small to medium volumes, it has a slope of -1, meaning the potential energy scales as a constant divided by volume. Taking the derivative, it suggests that the potential energy interactions will, on average, result in a decrease in pressure from ideal with a value that scales as a constant divided by volume squared. To test this, we can make a plot of log P plus A over V squared, where A is a constant, versus log V for the data in our simulation. This largely corrects the negative deviation in pressure at moderate volumes, suggesting we're on the right track. However, we still see an upward spike in the pressure at very small volumes. Intuitively, we might expect this to be caused by intermolecular repulsion when the molecules get near each other, pushing the pressure up. However, as we saw in the plot of potential energy, even when the molecules become quite crowded at small volume, the potential energy continues to decrease, suggesting that the spike in pressure at small volume must have some other origin. What van der Waals argued was that even though repulsion does not contribute significantly to potential energy, it still has the effect of preventing overlap of molecules in space. This effectively reduces the available volume for the molecules to occupy. One way to test this is to make a plot of log P plus A over volume squared versus V minus B, where B is an empirical constant representing the molecular volume occupied by the molecules themselves. As shown here, this straightens out the behavior almost completely. Summarizing, van der Waals argued that the behavior of a non-ideal gas will closely obey P equals RT over V minus B minus A over V squared. now known as the van der Waals equation of state. Returning to our plot of P versus V, we can see this equation does a pretty good job of explaining the behavior of our Lennard-Jones fluid for temperatures spanning 0.6 to 2.0 in dimensionless units. Although most of you are familiar and use more recent and accurate equations of state for non-ideal gases, such as the Redlich-Kwong equation, the van der Waals equation is remarkable in its accuracy given the very crude approximations behind it. What I also like about it personally is how nicely it lays bare the direct role played by potential energy interactions among the molecules in causing non-ideal behavior in gases and supercritical fluids. One key limitation of the van der Waals equation, as well as other cubic equations of state, is that it assumes the fluid will always remain a single phase. At temperatures below the critical point, it predicts that pressure must have sigmoidal behavior, decreasing, increasing, and then decreasing with volume. In reality, this behavior is never observed. Instead, the system splits into two phases. For example, here is the data from our Lennard-Jones simulation at a dimensionless temperature of 0.5 and 0.4. We see a flattening region in pressure versus volume that continues to get flatter as the temperature is decreased. This corresponds in the simulation to the formation of two distinct phases in equilibrium, as shown here for T equals 0.4. What this illustrates is that energetic interactions alone are insufficient to explaining phase separation. As we'll see in a couple of weeks, we also need to consider probability, as embodied in the entropy. Filling in additional data and also plotting pressure versus internal energy per molecule, lowercase u, we get the phase diagrams shown here. This makes it much clearer what's happening as we transform from systems of little or no potential energy to systems that have large amounts of negative potential energy. At high temperature and low pressure, we can see that the total energy per molecule U becomes equal to the kinetic energy T, corresponding to the case of zero potential energy. Here, internal energy is independent of pressure or volume, since the molecules are already so far apart they remain non-interacting as they get closer or further away from each other. In this region, the fluid also obeys the ideal gas law. At the other extreme, at very negative U, about minus 2.3 factors of epsilon below the kinetic energy, we have a dense fluid which exhibits sharp changes in pressure with volume. Sound familiar? That's just like what we saw for liquid water in the piston cylinder assembly. So this corresponds to a 2D liquid. In between, at lower temperatures, we see the system splits into two phases, a more dense liquid-like phase and a less dense gas-like phase, with horizontal isotherms in the region of volume and internal energy where both phases are present. Finally, we also see that as the temperature is raised, this two-phase region narrows, leading ultimately to continuous behavior above about T equals 0.5. This corresponds to a critical point, beyond which we only have a single supercritical fluid. What this exercise illustrates is that virtually everything we see qualitatively in the behavior of a real fluid has its origins in the potential energy interactions among molecules in the fluid. By extension, this means that the internal energy, which is a measure of these interactions, is a critically important property in how a fluid behaves at equilibrium. To apply this to real fluids, we need to find a way to measure this internal energy, as well as separate it into potential and kinetic energy. Unfortunately, it's not simply a matter of subtracting the temperature from the total energy as it was here. Real molecules have other ways to absorb energy individually besides translational kinetic energy, including quantized vibrations and rotations. However, as I'll show you next week, we can use first law analysis to quantify the total internal energy under different conditions, and use this to reconstruct the intra- and intermolecular components of this energy. This serves as a critically important first step in predicting equilibrium phenomena for real substances.